In this video, we'll talk about the midpoint and trapezoid rules for finding integrals numerically. So our first two rules that we'll approach are the midpoint rule and the trapezoid rule. Midpoint we've sort of seen before, but trapezoid is going to be a new approach to this. And they are both ways to give us a way to figure out the approximate area under a curve, given that we're doing a definite integral for this problem. So the midpoint rule is something that we saw way back when we were defining Riemann integrals in the first place. And that's taking the midpoint of each rectangle to be the height and using that area to approximate the area under the curve. So for notational purposes, we're going to write m sub capital N to be the midpoint approximation to the area where I take capital N rectangles to do so. So then how do we go about actually computing this for a given function? So let's say we have the interval from a to b, and I have my function f of x, and I want to approximate the integral of f over a to b with m sub capital N. How do we do this? Well, if I have a bunch of rectangles, for each one, I want to pick the height to be the function value at the midpoint, and we'll call c's these midpoints. So that'll be f of c1, f of c2, and so on. We then know if we have n rectangles, then our change in x is going to be b minus a, the total length, divided by n, which means then my sum formula for n rectangles is going to be the area of the first rectangle, which is delta x times the height, which is f of c1, plus delta x times f of c2, plus, and then all the way up to delta x times f of the last one, cn, or I can factor the delta x, plus f of c2 plus f of cn, where, again, delta x is b minus a over n, and then ci are all these midpoints, which will be at a plus I minus a half delta x. Basically, the point being these midpoints are all delta x apart. And where is the first one? Well, the first one is at a plus a half delta x. So it has to be the middle of the rectangle between a and a plus delta x. So here's our formula that you would need for doing midpoint approximations. And that is what you would need to know to do midpoint integrals. What if we want to go a little beyond this, something a little slightly more complicated? Not much, but slightly more complicated. We could think about doing trapezoids instead. So the idea is, instead of having a rectangle in each strip from a to a plus delta x, I make a trapezoid instead. And I connect the 2 points at each end to make a trapezoid instead of just picking the midpoint to make a rectangle. So it's only slightly more complicated than it is before, but the benefit here is it doesn't require us to find the midpoint of each interval. Right, before for the midpoint we had to find the midpoint of each side and plug it into the function. Now we don't need to. But the downside is our formula then becomes slightly more complicated to remember. So let's look at the formula for this, what it would look like. So let's start with basic geometry in trapezoids. If I have a trapezoid like this is my height h, this is my base 1 and my base 2, what's the area of this trapezoid? Well, the area is going to be h times b1 plus b2 over 2, basically the height times the average of the bases. Or the way we write this is h over 2 times b1 plus b2. Now, in the case of the actual trapezoid we're trying to find the area of, we have the following. There's my function. There's, for instance, one trapezoid. And we see that for this, the h is my delta x like before. My b1 is f of the left endpoint, and my b2 is f at the right endpoint. So if I take my n trapezoids, or my n slices, I then get n plus 1 endpoints. And if I have n rectangles, I have n plus 1 endpoints. I have x0, which is my a. I have x1, x2, x3, up to xn, which is b. That's n plus 1 points. This is the same sort of setup we had before when doing Riemann sums that were going to become Riemann integrals. So for trapezoids, we'll use capital T sub n, like we did m sub n for midpoints. So for my trapezoids, what's my first trapezoid look like? Well, the first one is going to have area, delta x over 2 times f at x0 plus f at x1, because that is the left end and the right end of that first slice. The second one is going to have an area of delta x over 2, f of x1, because that's the left end of the second trapezoid, plus f of x2. The third, delta x over 2, f of x2 plus f of x3, and the pattern keeps going up until delta x over 2, f of x n minus 1 plus f of x n. And if you look at this, you'll see that every term that I have shows up twice, once as a right end and once as a left end, except the far left and far right endpoints. So this only shows up once, this only shows up once, but everything else shows up twice, and then I can recollect my terms. So for a combined formula, what I get here is t sub n is a delta x over 2 that I can factor out front, times one copy of the first point, plus two copies of the next one, plus two of every other point, and then one copy of the last one. Right? So everything inside shows up as a 2. The endpoints show up as one copy of each, with the delta x over 2 out front. Remember this 2 out here, which we didn't have for midpoint because we're using a different formula. And if you want to write this to match what the book has, they just call these f guys all just the y points, which are the y coordinates of each point. So you can write Tn as delta x over 2, y0 plus 2y1 plus 2y2 plus 2yn minus 1 plus yn. And again here, delta x is b minus a over n. So there's the formula for trapezoid rule as well. It is slightly more complicated because of these extra 2's that show up places, but it doesn't require us to find midpoints. That's the trade-off there. So as an example, we'll compute m4 and t4 for the function f(x) squared on the interval from 0 to 4. So because it's 0 to 4, and I want 4 slices, they're at 0, 1, 2, 3, and 4, all the cutoffs. So let's now work these out. My delta x here is 1. That's great. So m sub 4 should be delta x times the function at the midpoints of each rectangle. So times f at 0.5, f at 1.5, f at 2.5, and f at 3.5. 4 rectangles, 4 things in my sum. But what is this? This is 1. This is a 1/2 squared, so a 1/4. This is 3/2 squared, so 9/4. 5/2 squared, and then 7/2 squared. If you add all that up, that comes out to an 84 over 4. We can do the same for t4. For t4, I'll get a delta x over 2, but now I only care about the endpoints, not the midpoints. So it's a y0 plus 2y1, 2y2, 2y3, and then y4. Note that here there's going to be 5 terms in the sum, not 4, because I'm taking all the endpoints, not just the midpoints. So it should be a 1/2 times a 0 plus 2 times 1 plus 2 times 4 plus 2 times 9 plus 16 is a 44 over 2, which is 22. So these two aren't the same, and that's fine. They don't have to be, but they're both approximations of the same integral. What's the actual answer here? Well, if I integrate x squared from 0 to 4, I get x cubed over 3 from 0 to 4. I get 64 over 3, which is 21 1/3. So it's between these two, and they're both not terrible approximations for only using 4 shapes to solve it out. So that's the idea of using the midpoint and the trapezoid rule to approximate integrals numerically. You can obviously do a lot better if you take a lot more rectangles, but for doing things by hand, this is about what you should expect to do. The main thing to do is know what the formulas are and how they are different from each other, to know how to apply in each given situation. And we'll talk about later why some are better than others and how they all work together, but as of now, these are just different methods to know for computing integrals numerically when you need them to solve problems.